Okay.
Hello, everyone. Welcome to the second tutorial on machine learning. Today we have Saman. He has been an advocate for helping students to learn concepts in AI, and I'm really happy that he's joining us for this session. I'd like to start with land acknowledgements. I would like to take this opportunity to acknowledge the traditional territories of the people of the Treaty 7 region in southern Alberta. The city of Calgary is also home to Métis Nation of Alberta Region 3. Today we have Saman. Saman is a senior applied AI scientist. He has extensive industrial and academic experience working with biomedical data, signal processing, medical imaging, natural language processing, speech recognition, and e-commerce data analysis. He is currently working as a senior applied scientist, working on enterprise level automatic speech recognition system. Previously, he was working with a team of brain scientists on brain-computer interface. Sam, stage is yours.
Thank you so much, Farhad. Thanks everyone for joining. First of all, I want to thank Dr. Malki for inviting me to this tutorial. Thank you so much. I appreciate that. It's a great honor to be here. I want to again thank everyone who joined this tutorial. I'm going to share my screen in a bit. Let me do that. Okay, I hope you guys see my screen. Does everyone see my screen?
Yes. And also, may I ask you to share the collab that you are working with, the link?
Oh, yeah, absolutely. Let me do that.
That also would be great for students who want to follow along and try everything.
Absolutely. I will send you this link. So if people want to also have access to the data set, they can do that. Here's the repository. So it's public. Everyone should be able to access it. If you go there and you basically download the Jupyter Notebook along with the CSV file, you should be able to run it at the same time too. So feel free to do that. Okay, so today's session is about some of the fundamental ideas in machine learning, basically random forest, decision trees, AdaBoost, and some of the concepts around those. I want to make this session a little bit more interactive, just also make sure people are not falling asleep in case I'm a little bit boring. So please feel free to ask your questions on the chat. I also try to ask some questions from you guys, and I would appreciate the responses in the chat. So you can just like put your answers in the chat and try to collaborate and try to communicate your understandings with me. And again, there's no right or wrong answer, so don't be shy to speak up. Again, that's how I learn stuff, by getting curious, asking questions and answering questions. It doesn't matter if it's wrong or right. Does that make sense to everyone? Okay. So we are going to this, if you see my screen, I put all these objectives here. We're going to have introduction to regression and its use cases in industry. We are going to have, again, another introduction to decision trees and random forests, AdaBoost, and some of the notes on bagging, stacking, boosting techniques, what is being used in the industry. I'll try not to get too mathy. I don't want to get into mathematics. Like I'll touch on some of the mathematical aspects of it, but I don't want you guys get into that like vicious loop of just getting into that side of project without knowing how it's applied in real world applications. So my focus would be on basically application of these algorithms, and I'll also talk about some of the mathematical theories behind them. And then we're going to talk about some of the hands-on examples, and we would have Q&A. And I have some assignments for you too towards the end of this notebook. So again, if you go to the link that I just posted, if you download the file with the CSV file, with the CSV data set, please feel free to just like run all the cells and complete these assignments later when the session is over. Do you guys have any question? Anything before we start? Excellent. Okay. So in machine learning and in the field of AI, you often hear people talk about different concepts. For example, classification, regression, supervised learning, unsupervised learning, and some of these wordings. So again, I want to put some effort in clarifying some of these concepts for you, because again, once you understand the fundamentals, you would understand how some of these algorithms work. So machine learning tasks can be gathered into 4 following categories. As you can see, we have supervised learning and unsupervised learning. Supervised learning, again, classification, categorization, and regression. So you can, again, classify these subfield of, for example, machine learning into these 2 categories. And we have unsupervised learning. Clustering, dimensionality reduction, or examples of such. So, and you apply basically some of these algorithms on different types of data. So we have discrete and continuous data. And again, just to make sure everyone is following, who can give me some examples of discrete data sets, data points? Just like put that in the chat. What do I mean by discrete? Anyone want to go ahead and... Okay, excellent. Let's see, there's some really good examples there, Mohammed and Andrew. Just I mentioned it, discrete is like height, temperature, or 10 minutes intervals, different objects. Exactly. So when we talk about discrete values, we talk about like a whole number. For example, 1, 2, 3, 4, so forth. Whereas, for example, continuous could be any range. It can have decimal points. So you can think about discrete. If I want to give you an example, a classification of dogs and cats, and you can represent them as numbers, 0 and 1, 2 buckets, 2 categories, you can count them. Whereas, for example, continuous values like height, you have sometimes decimal points, you can't count them. So it's like 1.25, 1.5, 0.25. So it's really important to understand these distinctions, because that's where regression comes into the scene. When we talk about regression, again, if you look at Wikipedia and so many other sources, regression is a way to measure basically relationships between a dependent variable, which is called the outcome variable, and one or more independent variable. So again, it's really important to have some good understanding of these keywords, because you often see them in the literature, in some of the Kaggle competitions, when you, for example, if you want to do practices on some cases there and so forth. So when we talked about independent variables, if you think about a data set, a CSV file, all the features, all the columns in your CSV files can be named as independent variables, features, or attributes. So again, they're basically used interchangeably. Be mindful of that. And we have one outcome variable. So the label, the results that we want to predict. So again, the task for classification, mentioned cats and dogs, is to go for 2 classes, 2 categories, 2 buckets. So again, discrete values. Regression, we're dealing with numbers, actual numbers, like height, like revenue, stock, basically value of the stock market, and all that kind of stuff. Does that make sense to everyone? Yeah, please feel free to ask your questions if in the chat, if you have any. So again, the terminology that we have, dependent variables or target variables are the variables that we want to predict. Independent variables or predicted variable, the variables that we want to basically, variables to estimate the dependent variables. And you often hear about outliers, multicollinearity, and basically homogeneity. So again, if you're not familiar with those stuff, if you haven't heard about those concepts or those words, don't worry, don't freak out. I'll talk about them. These are just, I put them here in case you basically observe them in the next sessions. For example, in your next tutorials or outside of these tutorials, if you read a paper or if you play around with some examples. So when we talk about outliers, we call anything that is out of the ordinary outlier. Something that doesn't follow the common sense, something that doesn't follow the common pattern that you would see in nature, in whatever subject that you're studying. So we call these data points outliers. We have something else called multicollinearity. And again, this is a situation in which two or more independent variables are highly related, are highly correlated. And then we have the homogeneity, and this is actually a situation in which the error term in the same is the same across all values of the independent variables. So just some common terms to know. And again, we have different types of regression. We talked about how regression goes for, again, continuous variables to basically predict an outcome, which of that type. But we have different types of it. We have linear regression. Of course, you've heard most of you have heard about some of these terms. Polynomial regression, we have decision tree regression, random forest regression, AdaBoost regression. And we talked, and some more. We talked about, today's session, we talked about these types of regression. So again, going to the first type of regression, which is always like the simplest one, and you see commonly, you've studied that in high school and in your college, you use it daily in your life, is linear regression. So what is linear regression? Again, you have data points, you have these features called X or attributes. Again, I go back to the example of that CSV file with the columns, different columns that you have. And I will call those columns features, attributes. And you have an outcome, a result that you want to predict. So the features, CSV columns X, Y, the outcome Y. We want to see what kind of pattern they inhibit. We want to fit a straight line to basically these data points. And this straight line would basically explain the relationship between these two variables, X and Y. So in order to do that, we use different techniques, but in its simplest term, this is called linear regression. And why it is it's called linear, because as you see, we put our assumption that these two variables have a linear relationship, not a non-linear relationship. Because again, at the top, when we talk about different types of regression, polynomial regression, for example, deal with this type of non-linearity in the data that you have. So that's the very first type of regression, and that's the simplest one. So as you see, in order to fit a straight line to the data, so again, this is the outcome, dependence variable, this is X independence variable. We want to basically show this case, like fit this line. So later, when someone gives us a new data point, a new feature or attribute, we can basically look at this line, and we can predict or basically tell that person the value that we can possibly accept. So again, I don't want to go into the mathematical aspect of it too deep. So if you're curious to see how this works, you can again read this basically introduction on how, again, linear regression works. But most of you are familiar with this, with these terms. We have this outcome, this Y, which depends on these independent variables. These are the features, for example, X1, X2, X3 in your data set. And you have an intercept B, And this is how you formulate this. So most of you have studied that in your high school and college, and you're familiar with it. So in machine learning, often when we want to basically we want to come up with an algorithm to predict something, again, based on different objectives, whether it's a classification, a regression, we have an error term because we want to be able to fit this line in the best possible way to the data points, right? Because, for example, if you're given all these data points and someone asks you, hey, in your perspective, how can I fit a best line to all these data points to explain their behavior? You can look at it visually and you can say, okay, based on basically my experience, based on what I see visually, I can fit this line like this, or can start from here. Or you can start from here, which is the worst case, because now the line that you're trying to fit to the data points does not follow the pattern that you would see. So we want to control this. And the way we control this is by the error term. So in regression, we use distance-based metrics in order to reduce the error and come up with the best fitted line that basically describes the relationship between these two variables. Does that make sense to everyone? Okay, excellent. I see someone asked a question. Thank you so much, Farhad, for responding to those. So we often, again, in machine learning and in AI, we call this stuff error functions and loss function. So again, as you go further towards this program, you get familiar with these wording, with these keywords. And loss function is basically the error term that we're trying to minimize. We're trying to optimize for the best fitted line that can describe the relationship between these two different variables, and for these two basically dependent and independent variables, right? And in order to do that, we want to minimize the error. So in linear regression, we want to minimize these distances. As you can see, we have fitted this line to basically to these data points that we have, and the way we've done it based on the distance that basically it has to all these data points. We want to minimize these distances. If we can do that, we can come up with the best fitted line. So we're optimizing for the distance in order to reduce the error and to optimize, to reduce the loss function. Sure. Yeah, we get there too. Like we'll get some more discrete examples. I just want to make sure you guys have a good understanding of this stuff, because everything is linear regression, basic regression. Even neural networks, as you go further towards the program, you see the neurons use the same rule. We have AX plus B and nonlinearity, like basically nonlinearity applied to the activation function on top of it. But the backbone, the underlying fundamentals is coming from linear regression. So having a good understanding of this would help you a lot in this domain. So again, for regression, these are the types of error that we're trying to basically go for. These are the type of metrics that we want to minimize and optimize based on. One of them is root mean squared error. So we want to reduce this, and it indicates how close the observed data points are to the model's predicted value. So again, I don't go to our I don't want to get into the mathematical aspects of it. We can again read more on this notebook, but feel free to ask questions if you have. So the main advantage of this metric, again, it's really easy to calculate. It's just like a distance-based metric, and you'll see how we can use scikit-learn to do that. It has no parameters to tune. It's very fast, and you can, again, it's really easy to use. Some of the disadvantages, it's really sensitive to the outliers. So again, we talked about what outliers are. Anything out of ordinary, something that is not following the common sense, the common pattern, based on the normal distribution or the commonality that you would see in whatever that you're studying. Is it in the society? Is it in that specific data set that you're following? Anything that is not following the common pattern is called an outlier. So this metric is really sensitive to the outliers. And the reason for that, we're trying to minimize these basically distances, right? So if you have an outlier here, it tries to minimize the distance based on that outlier too. So that's why this basically metric is really sensitive to the outlier. And I'll try to basically wrap this section and then answer the questions just to make sure we're following the time too. So here's again, linear regression. We talked about that using relationship between data points to draw a straight line through all of them. So for example, this is another examples of that. If you want to implement one in Python, it's really easy, straightforward. So the way we do that, again, the software libraries that you would use on and on. So NumPy, Seaborn, Matplotlib, usually import them at the top of your program. And that's how I would basically generate my data points. So I'm randomly generating numbers. This is my X, and this is Y. This is the dependent variable. This is all the independent variables based on these like random numbers that I'm generating. So when you plot them, you would see this scatter plots with these data points. Now, what I want to do, I can visually see that there's a linear relationship between a strong linear relationship between these two variables, right? As X goes up, Y goes up too. So as we move towards this direction, Y increases too. So visually, I can see there's a strong linear relationship. But what I want to do next, I want to fit a linear line to all these data points. And I want that line to explain this relationship in the best possible way. So linear regression, right? How would I do that? So again, scikit-learn would give you this really nice interface and API that you can basically use with different models. And one of the models is linear regression. It also gives you some additional metrics. You can calculate, for example, how much error you have for this like fitted line that is trying to explain the relationship between these two variables and so forth. So I'm using scikit-learn linear model and importing basically linear regression. I have this metrics to calculate basically how accurate that fitted line is. I'll talk about these ones later. This is for basically training, splitting. If I have a data set, you find a basically use case for this in the other section of this notebook. But again, what I do is, this is my model. I have this linear regression model, and I want to basically add the bias too. I want to have this intercept. So that's why I would set it to true. And basically in simple term, it's mentioning if you want to start from the intercept, like X and Y, like 0 intercept. If it's not set to true, it starts from, it will give it like a bias. So I fit this model to these data points that I generated. And when I plot that, you would see this nice line fitted to all these data points. So now going back to the questions that you guys asked, how does it know that this is the line that should come up with? Again, going back to this, it tries to basically reduce this loss function to reduce this error, which is like a distance-based metric. And I think it was Farzan who had asked about the squared error. So we have this basically actual y values for these data points, right? We know these coordinates. We know xy. The value of xy is y1. The value of, for example, let's go to this plot. The value of, for example, this data points, like x is 2, we have a y for it, right? But when we fit this line, the model tries to, for example, say if we have a data point here that we hadn't seen before, what would be its basically y based on these patterns that I've seen before? So it tries to predict for that. And the prediction we call y hat, the prediction that comes from the linear regression model. And we want to minimize, let me bring my whiteboard here. So we have y and we have y hat, right? So y is the actual value of the x's that we have on the y-axis. Y hat is the predicted values that's coming from linear regression, predicted values. I would actually call it actual values. Actual values, predicted values. So we want to minimize this, right? If we get it to close, if we get it to 0, it means that we have a perfect prediction, right? Based on the current pattern that we have. So what linear regression is trying to do, it's trying to minimize this, and it's trying to do it for all the data points. And we don't care about whether they're negative or basically positive, because this might produce like a negative number. That's why we square that to come up with a positive number, and we sum them up. And that is what we call square errors. Does that make sense, Farzan? And anyone? Yes, exactly. It's like a limitation. So our model is limited in its power to the amount that it can predict for new data points, the unseen data points, the data points that it hasn't seen before. So in order to minimize that, in order to basically get rid of that limitation, we want to, again, where did my whiteboard go? We want to minimize this. If we can minimize this to the best that we can, we would have a better model. And again, that's true for basically most of the algorithms that you see in machine learning, whether it's random forest, decision trees, linear regression, neural networks, and so forth. We want to minimize that loss function and optimize on the performance. So I see Andrew, are there models to clean the data set and remove outliers before doing a regression? I'll talk about all this stuff towards the end once we have covered because to me, most of them are just like about techniques, questions about techniques. So I'll give you answers to those shortly. Okay, so now let's look at an example to see how it works in some basically real world problems. So that was like a data set that we created, like based on random numbers. We generated some x's and we had basically this y, and we tried to feed like a best line to this to all these data points. So again, we use scikit-learn to do that. And again, when I talk about linear regression, you've again studied that in high school. It's basically represented by this: y equals a plus bx plus, again, this error term, or whatever the basically a penalty term. I'll talk about this one shortly too. But if you look at this part only, y equals a plus bx, x is your attribute, your feature in that CSV file, the column. B and A is what you try to you're trying to predict, to come up with. So once you fit this line to all those data points using scikit-learn, you can also see what the coefficients of those coefficients of the model are, and you can see the intercept and the slope. And the way you do that, again, you see we basically use this linear regression API. We have this, we fit that to these data points, X and Y. So now we have this model. Now, if I want to see the coefficients of that, I will call this coef with this underscore. So the first element will give me the slope, and I can also get the intercept. And it will give me the intercept and the slope of this line. Okay, so now going to another example. So again, if you follow along, I've included the data set for this one. It's just prices of the house, prices of the different houses based on different attributes. So it's called kchouse.data.csv. If you're using Google Colab, make sure you upload it to a specific folder, and that's how you can read it. For example, I uploaded this data set to this content folder, and I'm using pandas library. I'm reading this CSV file. So again, you saw I'm importing pandas as PD, and I'm trying to read that CSV file. So before talking about this part, if you basically read the CSV file and look at the columns, you would see this table. You would see all these attributes and features, and of course some rows. So houses df.head would basically return the top 5 rows of your data set, not all. And you would see you have ID, you have date, you have price, you have bedrooms, you have square feet, basically how big that place is, and so many other attributes, longitude, latitude. And based on all these features, we want to predict the price. So again, you look at this table, you look at this CSV file or data set, you know, you have all these features that you want to use as your independent variables, and your dependent variable, or Y, the outcome is the price. I want to see if I can do that. So again, in order to make this a little bit simpler, I would start with only 2 variables, price and basically a square feet.
I'm sorry for interruption. May I ask you to increase the font size a little bit?
Oh yeah, absolutely.
Perfect, thank you. And also,
yeah,
if you close the sidebar, perhaps we'll get a larger screen as well.
Oh, absolutely. Yeah, for sure. Thanks, Farah.
Perfect.
Is it better now? Can you?
Great.
Awesome. Let me actually decrease it a little bit. Oops. There we go. Okay. So now I am trying to make this a little bit simpler, and I want to, let me make it a little bit bigger. There we go. I want to basically predict the price only based on the square feet. I can theoretically do it based on all these attributes, but just like to give you a sense of how it works, I want to simplify this a little bit more. So if I plot this data set, you're using like a scatter plot, and you can see x-axis is the square feet, y-axis is the prices, and you would see here that I'm using a log scale. So again, I'm using a scatter plot to plot x and y. So this independent variable and this basically, and you can see this is normalized. So I divided by this minimum y to normalize it a little bit more. You can, this is optional, but it's always good to do. So I want to basically plot this. Who can tell me in the chat why I'm using a log scale? Why is it like a good practice to use log scale? Anyone, any ideas? What's the purpose of this log scale here? Logarithm scaling here. No one. Okay. We have growth by power of 10. The price versus square feet is exponential. Okay, I see some really good explanations. It's Shamus. Larger values generally have a larger difference between them than small values. So having a linear scale would result in a lot of empty spaces. Excellent response, Shamus. I'm sorry if I'm not pronouncing your name correctly, but that's it. So if we have some large values, again, outliers. Do you remember the concept that I was telling you, talking about? If I want to basically plot this data, if I have some really large numbers based on the price, there would be lots of empty, basically, spaces on this plot. So that's why it's always good to apply like a log scale to shrink that data points, make them closer, like together. It makes them linear. It put a restriction on the ranges, so they basically reside between like a specific range, and you get rid of those basically empty spaces on the graph. So it's visually more pleasant to look at. And also for different algorithms to learn off of. So that's why it's a really good pre-processing step for some of you, if you're wondering, to apply like some sort of linear scaling to the features that you have. And log is one of them. So now going back to this, by looking at this visually, you would see there is kind of like a linear relationship, right? There's a linear relationship between these two, as one is going up, the other one is also going up. This is not necessarily true all the time, but to most extent, that is true. So now we want to see if we can feed like a straight line to this. So again, these are some, for those of you curious, for example, for those of you who are interested in more data analysis or looking at the data set more, some of the functionalities of pandas, NumPy, you can go through all these snippets of codes in Jupyter Notebook and play around with them. It would basically, you can get some statistics of those. I'll try to talk about some of those, but for the sake of time, I might just skip some of them. So here we're trying to, as you can see, we're trying to, as basically some statistical analysis of this data, see if there's a pairwise linear relationship between each one of those features in our data set. And here we use like a heat map, a correlation map. And if you're using Pandas data frame, it's really easy to come up with these plots. So it looks really fancy, but it's really easy to produce. How do I do that? Again, you saw how I basically created this data frame using basically rich CSV from Pandas library. And I try to basically look at the top 5 rows and like look at all the columns. And now I can directly apply this .corr, which is like a function that would generate this correlation map or like heat map for you based on this Pearson correlation. So again, I won't get into that, but Pearson correlation is just like a correlation between two different variables, individual, like two different variables based on how significant the relationship is. If they have a strong linear relationship, as one goes up, the other one goes up too, then you would see these basically more aggressive colors, like closer to red. So as you can see, price has like a perfect correlation with itself. So again, it doesn't make sense to interpret this. But if you look at this square foot living and number of bathrooms, they have a significant correlation, 0.75. And the way you can basically interpret this is this, that if you increase the value of a square foot of the place of, for example, the house, the number of bathrooms should also increase, which intuitively makes sense, right? You can see again another strong correlation here. So what is that? This is like square feet above versus like square feet living. So if you have like a 2-story house or 3 stories house, if for example all the other like the top levels are bigger, then of course the living areas, the total living area would be bigger too. So that's why there's a higher correlation between these two. And sometimes you would see a negative correlation. So again, who can tell me what does negative correlation entails here? So for example, we have a negative correlation between, most of them are not super strong, but let's look at this condition and floors. There's a negative correlation between these two. Inverse relationship, exactly. So as one goes up, the other one goes down. Excellent, yes, perfect answer. So again, we can do this type of stuff before fitting your model, your linear regression model, or before choosing what type of model you want to use for your basically to predict the price. So these are some good pre-processing or statistical analysis before modeling. Just looking at the data to see the distribution, the correlation, and all that kind of stuff. We know we want to go for a linear regression. That's why we jump into that. This is another plot. This is called pair plot. So again, this shows distribution between each 2 variables inside your data set. So as you see, you can see the distribution between price and let's say this is the number of bedrooms. So you would imagine this should be like a linear relationship, right? Like as the number of bedrooms go up, the price should go up too, but this doesn't look like it. This doesn't look like a strong linear relationship. This is a strong linear relationship. You can clearly see as one goes up, the other one goes up too. So let's see what this variable is. We have price, and this variable is, again, square foot living. That's what we're trying to use as one of our features to come up with that straight line for linear regression. Okay, so again, here, what I'm trying to do, I'm trying to divide the data set into training set and test set. So again, I use train test splits, and I imported that using, again, scikit-learn. So again, you can follow along. It's up there. Scikit-learn model selection. It will give you this really nice API that you can now split the data between train and test set. And usually you train based on like a larger proportion of your CSV file, and you test based on a smaller portion that is left out, that the model hasn't seen. So again, this is out of the scope of the session. I won't get into that, but you can search a little bit on that side too. So now let's see what my split is. So I had that CSV file with all those rows and all the columns. I don't want to use all the records, all the rows for my training set to train, for example, this simple linear regression model. I want to use a subset of that to train, and I want to hold another subset later for testing to see how accurate the model is doing, basically performing. So you can see, basically I'm giving this houses DF, which was like a data frame that only has information about the square foot living, and that's again the X. uppercase X, the attributes or the features. Right now I have only one feature, and the price, the basically the label that I'm trying to predict, or the outcome that I'm trying to predict. And I also give it this test size, so I know I want to split the train and test set, right? So I'm going for 80% of my records, 80% of the rows should go to the train set, 20% of the whole data set, CSV file, should go to the test set. And I give it this like random C2, so I can regenerate, like reproduce this. Again, although I won't go into this, for basically, in order to present the data frame, the basically data points, for example, the attribute that you have, which in this case is, again, a square foot living, you have to do some pre-processing. You have to convert usually to NumPy arrays in order to, for the model to be able to get trained on, to basically be able to perform and train based on that feature. So here I had this data frame, pandas data frame, and I'm trying to convert that to NumPy array. So again, I use NumPy. I try to use as array, basically class, and I try to pass this data frame with this feature in it, square foot living, and convert that to a NumPy array. Now, after doing that, I want to create this like column vector, and I use reshape function. Again, if you're not familiar with some of those syntaxes, that's okay. Don't worry about it. The whole objective of this basically session is to get you familiar with the concept of linear regression, random forest, and all that kind of stuff, not this Python syntax. But the more you practice, the more you get used to it, and the more you understand what's going on. So I was talking about like scikit-learn and how it, again, it gives you the flexibility to use different models. Here we use linear regression, and we basically apply this linear regression model on this train sets that we had. And I try to test their performance based on the test sets. So you can see I'm trying to use the trained model here to predict some of the values that the model hasn't seen, to see, for example, how those values would look like. Are they close to what I'm expecting or not? I'll go through it in more details, but let's run it first and let's look at this graph, and it would make sense to you. So when you run this, you would be able to see, again, this was the same scatter plot, right? The price versus the square feet. And we wanted to predict the price based on this feature. And we want to be able to feed like a straight line, like a line to these data points. When I do that, when I use a simple linear regression to fit basically to the current data points, it comes up with this line. And it gives you these, like some of these metrics for errors. Do you remember we talked about how we measure the accuracy of this line by looking at some of these metrics? Residual, for example, sum squared of all the error terms. And again, I won't go deep into that because this is out of the scope of this session. But if you are more curious about how it works in terms of theory, you can follow this. There's a link in the Jupyter Notebook too. The most common one, root mean squared error. So again, that was the difference between the actual basically value for that feature, between the actual value and the predicted value. And you would be able to see that RMSE is basically this value. So again, RSS, sum of a squared, residual sum, is different from this root mean squared error. because they're slightly different in what they're measuring, but what you want to do, you want to decrease this. And again, scikit-learn will give you this flexibility to apply this function on top of this model and get the accuracy too. So in order to do that, if you see, I use this OLC else model dot score on top of the test set that I have to see the accuracy of my model. And again, if you want to import that, you would import it like this. You go to the top where I imported this. You have this metric. I think I imported the score somewhere. This basically the score comes from the actual implemented model, the linear regression that I imported. So again, I use the scikit-learn models, linear regression, to import this linear regression model. And when I apply this score on top of it, it gives me the performance of this linear regression model. So that's why I would get this 50% performance based on this model. When you look at if you look at it, it's not really good, right? It doesn't perform as expected. It's not what we want. So we want to basically increase this performance. We want to optimize based on this performance, and we want to decrease these error terms, these error rates. So that's our goal. That would be usually your goal when you're working with different machine learning models, AI models, and so forth. And if you're curious to see some of the basically predictions on some test sets, some test cases, we can do that too. So here I'm doing the same. This is the actual price, and this is the predicted price. The predicted price that's coming from this linear regression model. So you would see that the actual price is this, the predicted is this. So they're different. And as we reduce the error term, they would get closer. As we optimize the model for better performance, these two terms, the actual and predicted, should get closer to each other. And that's what we want. Does that make sense to everyone? Oops, I see some questions I missed out. Thank you so much for responding to some of those. Yes, it's dense. That's why it's represented as like a curve. Fitted line, but it's like a linear regression. So basically, you think about it as like a linear line fitted to these data points. Does that make sense? Okay. Let me know if you guys have any question. I've mentioned some points just to make sure we're on track with time. I won't go through all this stuff. Again, if you're curious to see how linear regression and optimizations on linear regression works, you can read more on this lasso regression, basically ridge regression, and so forth. Just to give you a summary of those, you would see that linear regression is really naive. It works based on basically a fitted line, a straight line, to basically describe the relationship between different independent variables and the outcome variable, dependent variable. So in order to regularize, again, that's another word, the term that you would hear in machine learning and in AI as you go through this tutorial and you read papers. The term regularization comes when you want to optimize a current function that is responsible for producing some predictions based on some sort of logic. You can think about it like that. So in order to regularize linear regression models to perform better, you would have these basically versions of that. We have lasso regression, we have ridge regression. So now the difference between these two, usually regression models works based on different attributes that exist in your data sets, right? So if you have, for example, that CSV file, you have 10 columns, 10 features, and based on those 10 features, you want to predict the outcome, price. So here we worked only based on one feature, which was the square feet. But if we had more features, if we wanted to include, for example, number of rooms or basically the year that the house is built and so forth, we would have more features. So lasso regression would measure the correlation between each one of these features, and it would give you an important, basically it would tell you that, okay, this specific feature is really close to, for example, the other one. So I'm going to shrink it. I'm going to get rid of it because you don't need it. Because getting rid of additional features in your data set would help the model to generalize better. So again, that's another term that you would hear more, generalization, meaning that you can perform, your model can perform very well based on all the population in your data set, not only basically specific points. Mohammed is asking a question, how do you know what to cut out to generalize? So again, when you use lasso, there's a penalty term, and it basically works based on the correlation of like different features that you have in your data set. Basically different features, it will give you different weights, and if the weights of those specific features are really close to each other, then you would know that one of these features is unnecessary, is redundant, so you want to get rid of it. So again, lasso regression would do it for you based on this penalty term, and the penalty term that you would basically introduce. Again, this is on its own. It's like, if I want to explain all this stuff, it would be a whole complete session. So I will go deep into that. You can basically read more about all this stuff in the same Jupyter notebook and get more context. But you can think about these two as two other versions of regression that adds this penalty term that can regularize your model, your linear regression model better, so it doesn't overfit. It can generalize better. And in order to do that, in order to use that, you have this regression.lasso that is imported from the scikit-learn. So again, you don't need to implement it from the scratch. If you go to the top, you would see that instead of linear regression, which is here, now I'm using lasso. So, and they're all imported from this linear model, basically class of scikit-learn. So I'm importing linear regression, lasso, and ridge. So again, these two different variations of this linear regression with the penalty term on top of it. So when I do that, let's go how it works. If you get any improvements in the performance, if you go here, you would see I would do exactly the same steps. After importing this from scikit-learn, I fit it to the train set, the training data set that I had, and I try to predict based on the basically test set. I also try to get the basically coefficients of the model, which is the intercept and the other coefficients if they exist. And I try to calculate again residual sum and the root mean squared error. So residual sum, again, as you can see, is implemented like this if you want to do it yourself. So you have the actual price in your test set, you have the predicted price, it's like raised to the power of 2, and you sum them. Whereas root mean squared error, you use numpy.sqrt, it's like a root squared, and you can use again this metrics class from scikit-learn, and you can use this mean squared error based on this price, like the actual price and the predicted price, to calculate this root mean squared error. And again, you can use get the model's performance based on this score function, based on this test set, and the actual test set that you have, and the basically prices that you want to predict. So when you do that, you see again the model performance is still 50%. So not much improvement in the performance of the model. But you also see this RSS and RMCE, the root mean squared error terms, but this is based on the lasso regression. Does that make sense? So Shishenza has asked a question, to make it straighter and to get a better line of fit or something else. Yeah, to some extent, if you want to abstract it and make it simple in terms of definition, regularization is making something more robust, reducing the errors. So again, in this case, in linear regression, when we want to regularize it, we add a penalty term to it. What it does, that penalty term comes in form of reducing the features, unnecessary features that exist in your data set. So again, you can think about it like that. And in order to do that, you would use, again, rich or lasso regression, and you can easily import them from scikit-learn and use them and have a comparison to see if you can get any boost in the performance of the model. Okay, so enough with the regression. Let's go to the decision tree and random forest and all that kind of stuff, all the fun part. Do you guys have any questions so far? Does everything make sense to you, or are you falling asleep, or you're bored? Okay, excellent. So let me get into the random forest and decision trees now. The reason I wanted to emphasize on linear regression was because most of the other algorithms use the similar underlying fundamentals. So if you understand linear regression, if you understand how it works, then different variations of it, again, they all use the same concept. They all use the same fundamentals. Random forest for regression use the same concept. Neural networks use the same concept. So once you get the gist of it, all the other stuff would make sense with some additional information on top of it. So now let's go to decision trees. As the name entails, decision trees, I like this example. Imagine, for example, you're out trying to buy tomatoes. You go to a store and in front of you, there are a bunch of tomatoes, right? Tomatoes come in a variety of shapes and sizes and colors, ranging from like small and round to big and like different shapes. You want to decide which one is better. So you want to come up with some sort of logic that, hey, which one should I pick? So you start with one fruit, you pick up one, for example, apple or orange. You look at its shape, you make a decision, and based on the next decision, you give it another branch. You would say, okay, the color looks good. What else do I care about? The size. Does the size look good? Yes. And then eventually you make your final decision. So you can think about it like this. Is tomato the right size? You would say yes or no. Say yes. Is the tomato right? Yes. So then I would come to this conclusion that it's a good tomato. If no, so then I won't go for it. Is the tomato the right size? No. So I won't even look at it. I would just like put it back and I would choose another tomato. So that's the concept of decision trees. You can think about tomato as individual attributes or features, or again, columns of your CSV file. For example, tomato could be the square feet of your house. Is the square feet big? For example, if it's a square feet more than 12,000, yes. Do I need 12,000? No. Do I need less? Yes. So see, you make different decisions based on different thresholds. So again, you can think about tomato as like different attributes, different features of your basically data sets. So that's the whole concept of the decision trees. So this is decision tree for classification. It's simpler to explain. That's why I started with this. I'll actually talk about how we can use it for regression as well, and how random forests use the same concept to basically fit. We talk about that straight line to explain the relationship, linear regression to explain the relationship between a square feet and the price. But now we want to add more features and use the same basically concept using random forest. So now let's see how decision trees work. As you saw, a decision tree is a flowchart like tree structure where you have nodes, internal nodes, representing different features or attributes that exist in your data sets. And you have branches that represents different basically decision rules. And eventually you have leaf nodes, like the final nodes that we will call leaf nodes. And they are the outcome, the label that you want to predict, the result that you want to predict. So again, in the house price, the outcome, the leaf node should be the price. All the other nodes should be attributes of your CSV file, of your basically data frame that you have, a square feet, number of rooms, etc., etc. So the idea is simple. The idea behind decision trees is really simple. You select the best attributes using attribute selection measure, ASM, to split the record. I'll talk about this one. Again, don't freak out if you don't know what this one is. You make that attribute a decision node and basically break the data set into smaller subsets. And then you keep going based on different decision rules to come up with these leaf nodes, your final targets, the label that you want to predict, the outcome variable that you want to have. So how do we come up with these nodes? Well, how do we choose these nodes and why do they even exist? Before doing that, I see some questions. So you could have branches on both sides of size with different checks. Oh, I see. Thanks for basically collaborating and talking to each other. I love that. I wanted to be more interactive, so this is good. This is good to see. So it seems the question is already answered. Thank you so much. So again, the question that I want to answer, how can I come up with these nodes? What would be my criteria? How can I decide what nodes I want to use? There's something called information theory, and it's a really beautiful concept. Again, for those of you who are interested in this, there's a whole, basically tons of papers. The idea is really old, but it's a beautiful field. It's called information theory by Shannon. I think I put a reference in this Jupyter note. You can find it and read more about it. But if I want to abstract it, if I want to talk about it in simple terms, you want to reduce variance. Again, what do I mean by variance? You want to reduce entropy. Again, so for some of you who are coming from engineering fields, engineering entropy is defined as a change in energy. And the more energy you have, the more entropy you have. In data science, machine learning, and AI, entropy is called noise. You can think about it in an abstract way, noise or variance. And the more you reduce this variance, the more you get into a cohesive, basically less noisy results. Yes, Valerie, that's Shannon entropy. So the core idea in decision trees, random forest use decision trees. I talk about in the next basically section. But the core idea in decision trees is this. If you understand this, that's it. We want to reduce noise, we want to reduce variance, and get to the basically less noisy attributes that can explain the outcome in the best possible way with not much variance. So in order to do that, we have different basically criteria, and one of them is information gain. The other one is gain ratio. The other one is Gini index. So again, I don't want to get into details of those because we don't have much time, but I want you to understand this, take this away, that all they try to do, they want to reduce noise, they want to reduce variance, entropy, to get to the attributes eventually that can explain the outcome in a very basically robust way, in a very confident way. That's how we can explain that. So again, going back to this root node, how do we decide on this? We know if we take, for example, age, if you have a data set and one of the attributes of my data set is age, if I pick that attribute as my root node, I know that age has a really high entropy, high variance. It has so many outcomes. I can build so many branches of this single attribute. And that's how I decide based on my root node. And the next step, I try to reduce this noise. So I would say, okay, if I go for the other attribute called weight in my data set, now this weight is reducing entropy, is reducing noise variance by 10%. So that's a good sub node. That's a good child node to choose from, to go for. And then from this, eventually we want to get into the leaf nodes, which are the actual outcome, the actual labels that I want to predict. So this is for classification. That's why you would see these classes, categories, like age, weight, and so forth. For regression, you would have the same idea, but you're working with continuous variables, continuous values, and we talked about what continuous values are. And this ASM metric, this measure of entropy, is a little bit different, and I'll talk about that too. But does that make sense? Is everyone on board with what's going on? So again, we go with the root node, we have this child nodes, we have this decision rules, and eventually we want to get into this Y hat that I talked about, the actual prediction, the basically predicted labels. What I want to do in regression, in basically regression trees, I want to reduce the error that exists in this outcome, Y hat. Do you remember when we were talking about linear regression? I talked about like error, how we can calculate that, like the difference between the actual values of Y minus the predicted values, and we would sum them sometimes, we would square them, some is like root mean squared error and all that kind of stuff. So the same idea exists in regression trees. So that's one way of reducing entropy, reducing noise. We use distance-based metrics like root mean, squared errors, and some variations of that to reduce entropy, to reduce variance, and get into a more deterministic, robust features, and finally outcome. So again, since we're dealing with regression, this was for classification. This is for regression. We use mean squared error as our measure of entropy change. let's see actually how much time we have. Okay, we have quite a bit of time, so we can be right on the track. So let's see how we can use that. Here, we're going to test, basically check this application of decision trees based on different data sets. One of them is the one I made myself. So again, it's a good skill to have. Sometimes if you're feeling lazy and you don't want to just go and look for like CSV files, you can quickly just like generate some data based on some hypotheses and assumptions and test some ideas. So that's what I want you to get from this Jupyter Notebook as well. So here I'm trying to get this NumPy array going. I'm trying to create this like data frame with like this data sets with these features: visual novel, 2D pixel art, strategy, and this value. So these features basically explain, represents different genre of gaming, different genre of arts for designing games, different games. So that's why you would see like RPG, sandbox, open world. Again, you don't need to know about the details of that. So these values, the first one is basically the production cost, and the third one is the profits. So for each one of these features, like asset flip, for this, for example, technology, the production cost is this, and the profit is this. For this one, the production cost is this, the profit is this, and so forth. So again, you can see we have continuous values. So we would basically reframe this problem as a regression problem. So let's see how we can use decision trees to come up with different, basically decision rules. We want to predict this production cost. We want to predict this, we want to basically predict the profit based on the production cost. So this is your dependence variable, this is your independence variable, and this is your dependence variable. This is the label or the target that you want to go for or predict, and this is the feature that you want to use for it. Does that make sense? So our goal is to predict this and use these features. So in order to do that, I want to use random decision trees. I'll basically import that from scikit-learn, that tree. I'll feed that to my data. So X is basically these values, the production cost, and Y, the Y that I want to predict, is basically the profits. So it's a very simple example. Once I fit that to the X and Y, now I have a decision tree, and that's as simple as that. So now I can use my basically trained model to predict on any other unseen data points. For example, this is a production cost of a different genre or like a different type of basically method. And I want to see what would be the profit for this. So I can do that. So if you run this, you would see that the model gets trained and you will come up with this predicted price. So if you want to get a bit of visualizations of what's going on, you can actually, this is the production cost, this is the profit, all these data points that you would see basically are the ones that you saw here. So X and Y. And this blue line is the prediction from this this decision tree. As you can see, it's really close to the data points. It's trying to mimic the exact behavior of these data points. Again, that's what we call overfitting. So that's a different term that you would hear. Overfitting happens when your model tries to mimic each individual data points precisely like the way they are. And we want to avoid that. So overfitting is basically what you want to avoid. So in order to basically deal with the problem of overfitting for decision trees, we go with random forest. So now one way to deal with that, multiple basically decision trees stack together to build a random forest, and I'll talk about that. And by the way, you can actually produce like a graph like this to see how the decisions are made. For example, you started with this feature at the top. The squared, again, I mentioned you're trying to minimize as you go down this path the mean squared error, which would again account for the reduction in variance or entropy for the classification. So you go for this, and then your decision rule is, okay, now should the profit be less than or equal of this? If you want to go down this path, then you have these attributes to explain this, and eventually you want to get to this leaf nodes with the squared error of 0 and the predicted values. So this algorithm is prone to overfitting, so it's better to simplify the minimum number of children per leaf node in advance and use cross-validation to find the values. So now we're going to go to the random forest. Random forest is basically use the concept that we talked about, decision trees, and they use basically use multiple decision trees to come up with the final prediction. And as you can see here, we have multiple trees and trees. They are trained in parallel, and eventually you average all the prediction and you get basically the final results. Does that make sense to everyone? I'm sorry, the way I'm rushing this because there's so many concepts that I recognize that I have to cover that was not part of this session, like overfitting, generalization. So I want everyone to understand some of these concepts, because if I understand, I want you to understand the motivation for random forest and the next AdaBoost, why they were basically developed to account for some of these problems that we're seeing, called, for example, overfitting, not being able to generalize very well. And again, the concept of generalization that we talked about, we want to mimic the general population. We don't want to mimic each individual data points. We want to generalize based on the whole population. So these are the concept that you should know. And once you know it, everything would make sense. So again, just to make it simple, random forest use multiple decision trees. And the important point that you should know, they are trained in parallel. So that's why you would see multiple decision trees in parallel. So the algorithm creates each tree from a different sample of input data. At each node, a different sample of features is selected for splitting, and the tree runs in parallel without any interaction. So these trees, which are basically these decision trees, don't have any interaction with each other. You subset your data sets into multiple, again, subsets. You would create multiple decision trees based on those subsets, and you would train each one of them in parallel with no interaction. So these basically decision trees don't have any interaction with each other, but eventually you would get a major vote. You would aggregate the result of all these decision trees to come up with the final predicted value. And that's how we can get away from overfitting, because now you have multiple trees that come up with different decisions. You can say, okay, majority of votes was about this predicted value, so I'm going to go for this predicted value. I'm not going to fall into this trap or this specific value. I'm going to generalize better. And again, it's very simple to use. So for this one, I'm using a different data set. As you can see, I'm again using this random forest regressor from this ensemble. Now you will see the class name has changed. So scikit-learn, you would use scikit-learn you would use this ensemble basically class, and you can import random forest regressor for your basically to calculate your error. Again, from the metrics class of scikit-learn, you would basically use mean squared error. And of course, when you want to train, you have to split your data set into basically the common way to do that is 80-20 or 70-30. Again, you get familiar with all these splits as you get exposed to different use cases. By the way, you don't need to have this data set on your drive. You can easily download this using this request library. So if you're following the same Jupyter notebook, if you run this, it should download this data set from this Google Drive for you. So you don't need to do anything. If you look at this data set, you would see you have petrol tax, average income, paid highways, population, and petrol consumption. And our objective, our goal is to basically predict this petrol consumption based on all the other attributes. So we want to go for this one. Again, you can reframe this as a regression problem because this is not classification. We're not going for passes or categories. We're going to for continuous values. Like, so the first thing you would do, you would like split your training set into, you would split your data set into train and test with 20% split, train 80%, test 20%. And that's how you would do it. Random forest regressor. So now we're going to talk about these parameters of this function. You have max depth for number of estimators, and of course, random state is to reproduce the results again. It's like random seed. But what this does, again, you understand the concept of decision tree now. That decision trees basically work, let's go to this example again, work based on this node, root node, and it goes into different layers, different depths. So this is depth 1. Usually people either call it depth 0 or depth 1. In literature, you would see depth 0 is often used, but this is depth 0, depth 1, depth 2, and so forth. And you can restrict these decision trees to go up to a specific depth. If you don't want to prune, that's another keyword that you would hear. Prune means going all the way to the last depth. So if you want to have a cutoff here, you would explicitly mention that I want the max depth to be 4 or 3. And that's how you would do it. So that's why you would use this max depth 4 here. For this specific problem, I want to go up to this basically depth. I want to use n estimators. Who can tell me what this entails? Exactly. Thanks, Farad, just for clarifying that. Anyone, any idea what this n estimators entail in random forest regressor? Number of trees, exactly. So you can use either 1. If I use only 1 number of trees, what am I doing? This is not a random forest anymore, right? This is like a single decision tree. If I want to use multiple of them, then now I have a random forest. So I can either use 1 number of estimators, 2, up to like as many as you want. But the decision comes with experiments. You have to experiment. You have to see the effect of number of estimators on the performance and decide. So again, on its own, that's a completely different topic. But number of estimators is the number of trees, decision trees. And there we go. You feed that to your train sets, and you have a trained random forest regressor based on only 4 layers, 4 depths, 10 number of decision trees, trained in parallel with no interaction. And now you can predict based on the unseen data. So let's see how it works. This is your root mean squared error, 95.87. On its own, it might not have an explicit like units or meaning. What you want to do, you want to decrease this. You want to basically reduce this. But another way to basically evaluate that is that score function to see the accuracy of the whole model. So you would see the accuracy is 91% based on, based on 10 number of estimators and max depth of 4. So now if you change this, let's say I would go max depth 10. Let's go max 10, for example, 2. I'm going to run it. Let's see how things would change. So this changed a little bit, not much. Let's go for like a higher value. Let's go 10. You see this increased a little. Let's change the number of estimators now. So now we went for max depth 10. We don't see any like significant changes. Let's go for number of estimators. So I want to show you how we can experiment with this stuff. Let's go for 20 estimators, 20 random like decision trees. I'll do that. And there you go. You would see that the error increases. So another important point, not all the time, basically increasing the number of decision trees would help you to improve performance. So you have to be careful about that. I have another function here, which I commented that. So if you can experiment with different number of estimators within this range and see how the results would change. If you run it, we get like a scatter plot. It basically trains multiple decision trees, random forest based on different number of decision trees, and you would see this is the number of estimators. So not necessarily changing the number of estimators would help you reduce the error. So on the y-axis is your error. You would see somewhere here is basically the minimum error that you're getting. As you're increasing it higher and higher, you're getting the higher error. And then you can basically, as I mentioned, predict on some actual test cases too. I have another use case here, but for the sake of time, I won't talk about this. I would go to the last part, basically AdaBoost. This is for yourself, just to experiment a little bit more on like a different data set. This is on the same house data that you have, like you have the CSV file, so you can experiment and see the results. So now what is AdaBoost? You saw, for example, random forest. You saw decision trees, how random forest basically use multiple decision trees in parallel with no interaction to overcome the problem of overfitting and generalization. We want to generalize, have a better generalization. We want to mimic the general population more, and we don't want to fall into that trap of bias, get bias towards specific data points. So AdaBoost came to help with that. What does AdaBoost do? So AdaBoost is like a boosting mechanism. Again, don't worry about like these fancy words. The boosting here entails the training does not happen in parallel. So you train, for example, a decision tree with a fixed, basically max depth, usually 1. We would call it the stops, and I'll talk about that shortly. And you would fit the output, the result of the first output to the next. So that's where the keyword boosting comes from. The next basically stage would get a boost from the result of the first one, and so forth. It's like a step. So AdaBoost is categorized as a boosting mechanism, whether although random forest is categorized as, again, if you go here, I want you to also get familiar with the terms. Basically, I put that here. Random forest is like a way we call bagging. So bagging is an ensemble method that uses multiple basically algorithms in parallel and then gets a major votes. So these are of type bagging, basic ensemble methods. Whereas boosting is where you have, for example, the output of the previous step going to the next step and so forth. So again, add a boost is of this category, is a boosting method. That's what we call boosting. Random forest is a bagging method, subcategory of that basically methodology. So again, I put some of the math background, basic underlying theory here. I won't go into that. For those of you who are interested, you can look it up. But the interesting part about AdaBoost, we use these small decision trees. So it doesn't have like as much depth. It's like smaller in size, usually one, and we call it a stump. It's like one root node and like 2 leaf nodes. But we have many of these ones, many of these stumps. So the result of this stump gets weighted and goes to the next one, gets weighted, next one, and so forth. And we call these ones weak learners. Why do we call them weak learners? Because they're shallow, they're not too deep. They can't basically extract the complex features. They're really small and simple, but they're powerful when they work all together. So that's the leverage that AdaBoost would give you. And again, the way you can use it, we have AdaBoost Regressor, and it comes from, again, the ensemble class of this scikit-learn. Of course, for your stump, which is like you have to create like a base decision tree, right? Because AdaBoost also uses decision trees, but it's boosting them, like uses the result of, for example, one, weights them, fits them to the next one. So you want to also import decision tree regressor from this tree class of scikit-learn. And now this is how we create it. The max depth is 1. That's why we call it stop. Again, this is, you can play around with it. Like there's no issue. Like it doesn't give you an error if you increase the depth to 2 or 3 or like any other higher depth. But you should know that the main idea of AdaBoost comes from the stop, the shallow decision trees. So that's why we put 1 in here. So we have 50 estimators, number of estimators, decision trees. The base estimator is this decision tree with max depth 1. So learning rate is the mechanism that would weight your basically result that's coming from the stop. It weights them based on how accurate the results are. And again, here, now everything is making sense to you. That's why I started with like linear regression with basically different techniques to increase the error rates, mean square error and all that kind of stuff. So AdaBoost is using the same concept for weighting. So you see the pattern. It gets repeated over and over and over again. So for weighting, we want to actually check the basically accuracy of the stop, the result of the stop, weight them, give the results to the next stop. And in order to do that, we use the same metric-based methodologies, mean squared error, and so forth. And again, I won't go deep into that. You can read more about it here, but you can see this is exactly the same concept with some additional weighting on top of it. So this learning rate would help you do that. And again, everything else is the same. You feed that to the model, you predict based on your test set, and you would see, that's the interesting part, the accuracy decreased to 86%. And this is the accuracy on basically test. Whereas the accuracy here was 90 something percent, right? So it would be interesting to see this is less accurate, but more general. Whereas random forest is more accurate now, but less general. So if you collect more data points, more test basically data points, and you fit it to this, for example, AdaBoost regressor, AdaBoost might be able to generalize based on the whole population better for you compared to this random forest. So that's another important point to understand, that sometimes higher accuracy doesn't mean it's a better model. You want to consider generalization. You want to see how generalizable that model is based on more unseen data points. Sometimes it's better to sacrifice based on a less accurate model, but more generalized model. To some extent, based on a threshold, like 80 something, but more generalized model. So these are the stuff that you have to consider and know and be aware of, and you get more used to it once you see more use cases. And I think that's the end. I think I went over the time a little bit, but sorry, there's lots of stuff to cover. As a summary, we talked about regression, continuous values. We talked about different types of regression. We talked about an important concept called ensemble methods, bagging, boosting. Now you know what bagging is. Bagging is parallel trees. There's no interaction between them. Boosting the results based on sequences. You saw that regression uses metric-based measures to calculate errors. Classification uses another type of error. And that actually wraps up today's tutorial. There's another assignment here in case some of you are interested in checking and basically completing. Thank you.
Perfect. Thank you. Is there any questions from the audience? Feel free to unmute at this point and raise your hand, unmute, and ask. Or if you prefer, feel free to share on the chat.
I see lots of thank yous and no questions. Guys, please, like, either you didn't understand anything or you understand, you should everything perfectly. Okay, I see Anna says, wouldn't a neural network be a further generalization of all these techniques? Well, that's, again, that's why these techniques basically evolved. The people started working traditional statistical modeling, and then they moved more towards this neural networks that can detect more patterns using convolutions, use more activations like nonlinearity on top of these linear regression modeling to capture more patterns and basically avoid overfitting. But again, that doesn't guarantee, that doesn't mean that neural networks don't overfit. You have to be careful. There's a trade-off here. But yeah, that's.
Okay, perfect. I think there was a few perhaps questions that we missed to answer. One of them was regarding reshape function and what does -1 mean?
Oh, gotcha. Let's go to that point. Yes, reshaping is really important, especially when you want to basically prepare your data frame to fit it to the model. You can't do it directly using pandas. You have to create a NumPy array and reshape it. So what reshape does, I think it was here. Let's go to, there we go. Should be somewhere here. So again, as we get there, reshaping basically helps your NumPy array, there we go, to basically get presented in a specific way. So let's say -1, it helps you basically collect all the values and present it as like a column vector and in one single column. So that's why you would see these columns like a column vector with all these rows. And that's how we can basically fit it to the linear regression model and get predictions back. The same with prediction, the same with the label, why? So you want to make sure as you play around with the Jupyter Notebook too, once you create your train set and test set, if you fit it directly to this model, if you fit it directly to this fit function, it will give you an error. And again, it would mention that the dimension doesn't match. So now when you get that error, you have to deal with the dimension. Reshape is a strong, powerful function that helps you to do that. And again, you would use it over and over again, but this -1 is to do that, to represent as a column vector with all the rows, single column.
So in general, we can say that when you use -1, actually you tell the reshape function that's inferred. For example, if you have a vector of 1 by 8 and you want to reshape it as either you can say you want to convert it to 8 by 1, you can say reshape as parameter 8 and 1. In that case, it knows that, okay, I want to have 8 row, 1 column, or instead you can say -1 and 1. So -1 means infer it as needed. So it will be some calculation done by reshape, and they realize that, okay, this should be 8. Okay, Andrew has a question. Andrew, feel free to unmute.
Hi, yeah, I was wondering in the topic of random decision trees, if instead of having a bunch of decision trees working on the same feature, if we could have like a bunch of different trees working on different features. So for example, to predict the price of the house, could we have one decision tree working on the number of bathrooms and one working on the number of like square feet?
Absolutely, and that's the power of like this decision tree. And as part of it, I didn't go through it, but I basically put it as an assignment for you. You have to do this. So that's each decision tree. That's why I mentioned you have this whole data set, Andrew, and you basically subset your data set. You create subset of that. You create a bunch of decision trees that work based on different attributes that exist in your data set, to eventually come up with a prediction for that one single label. So you can add more features. Let's say instead of a square feet living, you can add bathrooms, bedrooms, year built. And now the decision trees, for example, let's say you have 100 estimators. These 100 estimators are initialized randomly, and they go based on like reducing of the information variance based on different combinations of attributes and features that you have. So it leverages those. That's why they are trained in parallel in random forest. And eventually you get the major votes because you are training based on multiple combinations of features. And eventually the one that has the major votes, we would basically assert that you should go with this prediction for that label. Mm-hmm. Does that make sense, Andrew?
Yes, that makes sense. Thank you.
See, I mean, Reza has asked a question. In general, for the reason that we're using lasso and ridge regression, which one is more accurate and useful to use? Is there a way to use both of them in order to get lasso and ridge are really important concepts. You see them being used in neural networks, all basically the different deep models, and the power of them comes with that penalty term, regularization. So you can use a hybrid version of those two. Usually, you should choose basically which one you want to go for. Lasso basically shrinks the parameters directly to 0. So it basically eliminates the specific features on the spot for you. Whereas reach makes it super small. So you can still leverage the features. They're not eliminated, but they get less weights. But so these are the trade-offs. So in some cases, for example, in dimensionality reduction, you have a data set with millions of columns, and you know those millions of columns would not be used for you. So lasso would make sense because you want to just like shrink most of these attributes to 0 and use just the most important ones. Whereas like in some other cases, when you want to keep all the features, you don't want to get rid of them. But you want to leverage the penalty term, you would use ridge, because that would regularize basically the model based on less number of attributes, but more important attributes weighted to them. Does that make sense? Exactly. Yes, Amraz.
Okay, perfect. Also, another question came up regarding the mean square error. Why we use actually we use some measure that actually convert this errors to a positive value. That's important because in most cases, we want to minimize errors. So error happens if you predict, for example, for something that the true value is 1, you might predict 2, or you might predict 0. So in that case, depends on what you predict, you might get a positive or negative value. And if you don't make this this estimate of error a positive value and then try to minimize it, actually model learn to, okay, I just try to, when I need to predict 2, I go with a smaller value. So that's actually not a good approach. We should make it absolute value or something positive. And why a score value? Actually, by doing a score, one nice thing about it is that you penalize big errors, and that's a good thing. So you make the model to not make those big mistakes. And that's another aspect of it. It is one loss function. There are many others. You learn many of these loss function in different session of the class as well.
Perfect answer. Thanks, Farhad. That was great.
Also, another question came up regarding a loss function, Mahalanobis distance, actually the distance function that can be, so why we use that? It's a distance function. Perhaps you might see it in the future. There are many loss function, many distance function for calculating distance between data points. These data point might be a data point in the search space, input space, or in the prediction space. So Mahalanobis distance is actually decided. It's good for a situation when you have data points or features of different scale. In Mahalanobis distance, we use the covariance of different data points, so the dependency between data between features, and that can help us to actually do better for those cases. For something, whenever you use Euclidean distance, something that you have seen here, for example, and it's a common distance we use in real life. For those, we always need to make sure that our variables are in the same scale. So some normalization or standardization is important. Otherwise, the error will be actually dominated by one large feature. For example, if you go with a price, which is price for a house, which is in a million scale, and you have other number of room, which is 1 or 2, in that case, many of components that are large, many of features that are really large value negatively affect the performance of the model. And because of that, whenever using something like linear regression or technique like that that rely on Euclidean distance, for calculating error, we do work hard to make sure that the data are somehow normalized, and that's the requirement for applying linear regression. Any other question from the chat? That's Farzan mentioned that why we don't discuss about the classes of and the dimension of the data. I think that's a very good things to cover. We starting next week, we'll have mentors working in the Discord channel, and they cover some of those contents. Please feel free to go in the Discord channel. I assume at this point everyone should be signed up there. Share, ask your questions, and also help others with answering. It's a safe environment for learning. Okay, also tomorrow we'll have classification session. Some of the content that we went through it today, they show up again as a classification case. So it's a good recap of these concepts covered today. Another thing that I like to highlight is that we will be actually building, we are trying to help students. Perhaps you guys will be the first group to get involved to build a AI research club. So this is something we want to help you guys to build the club and ratify it. And will be hopefully a community that you can actually design different activity for you, and will have more opportunity to help a student in that regard as well. Feel free to discuss these things in the Discord channel, and we'll provide you with more information the coming week. Is there any other questions from our guests? Okay, perfect. So please join me to thank Sam. He did a great job and covering a lot of ground, actually, a lot of concepts. Very helpful and very useful. Thank you so much.
My pleasure. Thank you so much for Farhad for inviting me. Absolutely, my pleasure. Thank you, guys.
Thank you, everyone, and have a great day.
Have a great day, guys. Take care. Bye.